Hello, kids, coming at you from the Venditto haven of peace, love, and summertime physics. And we are here to show you how to do 3 homework questions, specifically numbers 83, 30, and 32. And so 83 is the one in the book there that deals with a spinal tap, and the only reason I really had to do this one is because many folks will tell you one of the greatest movies of all time is Spinal Tap. It's a fantastic movie. I highly recommend you watch it. It won't help you understand physics, but it will help you understand me, which the debate is raging as to which is more difficult. But anyway, tonight I'm going to rock you tonight. So, what is a spinal tap? What the docs do, lay you down on your back, and they'll literally jam a needle into your spine. And what then the pressure of the fluid going from your brain and through the spinal column will then allow that liquid to elevate itself to a certain height. And if it goes up to a certain height, then it's pretty easy to calculate the pressure that the fluid is exerting on that liquid to push it up to H. And in this particular question, the book told you the height is 160 millimeters, which you know again is 16 centimeters. It's also 0.16 meters. All right, so if you want to know the pressure that is pushing that fluid up to a height of 160 millimeters, then what you need to know is the formula for pressure, which I'm sure you all do by now. Pressure is simply rho GH, the density of the fluid, times what planet you're on, times how high up it is elevated. So the density of the cerebral spinal fluid is that of water. They're going to call it 1,000. We're hanging out on planet Earth. The height, again, given in the question, 160 millimeters. I'm not going to call it 160 millimeters, though. I'm going to call it 0.16 meters. And so then the pressure that would be in pascals is going to end up being 1,570 pascals, 1570. In chemistry, you're probably more familiar with kPa, so it's the same thing as 1.57 kPas, because that K just means 1,000, move it over. So same thing. So that's all I want to know. What's the pressure of the cerebral spinal fluid in pascals? 1570. All right, then the rest of the question is simply, all right, what would that pressure be if you converted it into what I jokingly call bank machines and ATM, 1 atmosphere? And so what I'll do is start with that number, 1.57 kPa, and if you divide that by 101.3 kPas, convert it to atmospheres the way you guys remember how to do in chemistry, then all we're doing is taking 1 and dividing it by 100, which will turn it into 0.01, and this answer is 0.0156 maybe, or 55. It depends on how you round it, but that many bank machines, that many atmospheres. If you wanted to turn it into millimeters mercury, remembering standard pressure in millimeters mercury is 760, then what you'll do is take that same number, the 1.57 kPas, divide it by 101.3, but then multiply that by 760, and what you'll get is 11.8 millimeters mercury. All right, so about 12-ish millimeters is how high it would be if they spinal tapped you with mercury, or if your spinal fluid were mercury, which it clearly isn't, and it's 160 millimeters with your spinal fluid being water. Okay, and that number kind of makes sense. The density of mercury is 13 times as dense as water. Since that density is 13 times the number, the height will only be about 1/13 the height there. So if you divide that by the density, you'll end up getting the number you're looking for. But anyway, there's that. Now, what does it mean if the doctor or somebody presses down on your spinal fluid or on your spine right here. What Pascal's principle tells us is if somebody pushes here, applies pressure here, that pressure is evenly distributed throughout the fluid, which means it should cause that height to elevate. Should. Unless something's blocking that spinal fluid or something is blocking your spine entirely. So if that does happen, and if you push down here and this doesn't move, that's bad. That's an indication of maybe something is blocking the spine or interfering with your spine. It could be a bulging disc between vertebrae, which has to be very painful. I don't know, I'm very lucky, I haven't experienced that. Or even worse, if there's some sort of tumor growing inside your spine, which would then prevent the pressure from being transferred here. So they'll apply pressure here. If it doesn't go up, then they'll move over here, apply pressure, and keep applying pressure closer and closer until, I apply it here, it did elevate, so whatever blockage must be behind it. But anyway, the spinal tap question, again, simply for the fact that it dealt with a spinal tap. And the next one I did, we said it was number 30. And this is the one that deals with you floating in the Dead Sea, which is very, very salty water. So the density given of this very salty water, 1,230 kilograms per cubic meter. And we'll learn in our next question the density of typical sea water or ocean water that is salty isn't even close to that. So this Dead Sea, which I agree I wouldn't want to float in something called the Dead Sea. They could have picked a more flattering name, but anyway, that's what it's called. Very, very salty water, 1,230 kilograms per cubic meter. What they're then saying is, hey, the density of you when you exhale, when your lungs are empty, is a high density because you have a very low volume, 1,020 kilograms per cubic meter. Typical number, different people are different. If you take a nice big deep breath and then hold it, then your density will decrease, which will allow yourself to float more easily to 945 kilograms per cubic meter. All right, so then this says, okay, what can we do now to sum the forces to say, okay, what percentage of you is going to be above water, what percentage of you is going to be below water? And it says to treat this like a Newton's second law problem, which I want you to, again, remember, always when you can, treat them like a Newton's second law problem because, well, gosh, it's a Newton's second law problem. So how many arrows do you see? When this person is floating on the water, there are two arrows. There is the FG of this person, and there is the FB of the person, the buoyant force and the gravitational force. And these two items will add up to nothing. It's just like life. Yay. What that means is this person isn't moving in the y, so their acceleration in the y is 0, so this whole term goes away. So the sum of the force in the line equals may. May does not get to stay. May goes away, which means it's equal to the acceleration of the y is equal to 0. So how many forces in the y are there? There are two. The upwards one is buoyancy. The downward one is gravity. So this will be an FB minus an FG is equal to nothing. So then that FB is equal to the FG. Okay? Now, a buoyant force, you hopefully already know, is the density of the liquid that you're submerged in times the gravity of whatever planet you're on times the volume that happens to be submerged, the V sub, the rho GV. This then is equal to the force of gravity on this person. The force of gravity on anything is an M times G. Okay? Now, it did not give you a mass of you. But one of my favorite sayings is don't let the fact that you don't know something prevent you from doing something. Just ask any politician. So what you'll do with that mass is go up to this density formula and just replace it with an expression for mass. So if density is mass divided by volume, what you'll do is rearrange it so that you have mass by itself. It's density times volume. So it will look identical to this side of the equation. The only difference is it's not going to be the density of the liquid, it's going to be the density of you which again was given in 2 different examples. So what I will do is replace this m with a rho of u times a v of u times g. So it's just a different arrangement of this side. It's a rho gv is equal to a rho gv. Same thing. Okay, now what you can tell then is it doesn't really matter what planet you're on because the g's cancel. And we're comparing now the density of liquid, the volume that's submerged, the density of u times the volume of u. All right, now this question wants to know what percentage of the volume of u. Okay, so the volume of u is what we're going to use as a reference. So what we'll say is, the volume of u is what we give our answer in terms of. All right? So the volume that is submerged is what we'll solve for in terms of the volume of u. So the volume that's submerged in terms of the volume of u. What that means is I will take the v sub and set that equal to the density of u divided by the density of the liquid. So all I'm doing is moving that density of liquid over and then multiplying it by the volume of u. So whatever the volume of u is, it doesn't matter, the total volume. What matters is the ratio of densities times that volume of u. Okay? And it'll make sense here just in a second, but the density of u, it doesn't matter which one of these you want to use, the 1020 or the 945. They're both done exactly the same way. We can start with the 1020 kilograms per cubic meter. That's the density of u divided by the density of the liquid that was given in the problem, which again, very salty water, 1230 kilograms per cubic meter. Those units cancel, and it's this times the volume of u. That much of u is what is submerged. Okay, so this much of u is what is submerged. So it's that ratio of densities. So what 1020 divided by 1230 is ish 0.768. That's the decimal version. So 76.8% of u is submerged. So the percent that is above water is 100 minus that, and it ends up being 0.232 is of u is now above water. So 23-ish% of u is above water. 76.8% of u is submerged. And then you can do the exact same thing. Just replace the number 1020 with the other density given in the question, which was 945. So if I take 945 and put it right there, then the answer changes a little bit. Whoops, which means I gave you the wrong answers, didn't I? Geez, this 1021 is not the 0.768. Sorry, the 1021 is the other one. It's the other answer. I'm sorry, I had them written in the wrong, but it's 0.829. Sorry, I was looking at the wrong number. So 0.829 when you're 1020, which then makes it 17.1%. or 0.171, which is 17.1% of the volume of u is above. That's if you're 1020. If you're 945, then those are the numbers I just wrote. Then that's when it's 0.768 of u is above water, or is below water. Sorry, that's V submerged. That's V submerged, 0.768, which means the volume above is 0.232. 23% of u is above water when you have the lower density, the fuller lung, full of water, or full of, geesh, not water, that would be bad, full of air. All right, so there's that one. Now, a more complexercated one, which I believe is a pretty confusing problem, and that's why I'm showing you how to do it, is number 32. Plus, it's one that doesn't have an answer in the back of the book, so I figure this would be a good one to show you how to do. This is one that deals with you on a life raft, all right? So number 32 has you floating on a block of styrofoam as a survivor on a life raft after a ship has a tragic accident, whatever. It's made of styrofoam. The dimensions of the raft are 2 meters by 2 meters, and the total height of the raft is 0.09 meters. Of those 0.09 meters, only 0.024 of them happen to be below the surface of the water. Okay? And so this question then tells you the density of normal sea water is only 1,025 kilograms per cubic meter. Again, compare that to the question we just did in the Dead Sea, where it's 1,230. So that Dead Sea is considerably saltier than typical salt water. All right, but anyway, there's that. So if you're floating on a raft, you have a mass of 62 kgs. This raft is that dimension, and it's this much of it is what is submerged. Then it says, okay, let's move on here. Let's start doing some math. And it says, all right, first of all, draw a force diagram. How many arrows do you see on this system? And this question is a little confusing because the first part says draw it with the person and the raft as the whole entire system. And if that's the case, fine, then there's 2 arrows. There's a buoyant force holding this whole entire system up, and there is a force gravity, which I labeled total, FG total. That would be an answer to part A, but then part B in this question has you then separate and calculate different parts using that gravity total broken into its 2 parts. The force gravity of you and the force gravity of the raft pointing down with that same buoyant force pointing up. So it just depends. If some of you give this as the answer, I can't call it wrong as long as you label it total. And if some of you give this as the answer, I can't call that wrong either as long as you have it labeled correctly as the gravity of you and the gravity of the raft. All right, so there's that. Part B then says, okay, write a formula for Newton's second law, which again, sum of the forces of the y equals ma(y). That's Newton's second law, sum of the forces equals ma. To then figure out what that all adds up to. Again, if you're floating, that means you're not rising, you're not elevating. May goes away. May is equal to what war is good for, which is absolutely nothing. All right? So, buoyancy minus the gravity of the raft minus the gravity of you is equal to the number of friends I have. Okay? There's part B. Part C then says, okay, let's figure out what that buoyant force is. The buoyancy equation, again, is the density of liquid times gravity times the volume of that object that has been submerged, the amount of liquid that's been pushed away. Remember, another way to say rho v is simply the mass of the liquid times g, which is the weight, mg. So again, if you oftentimes hear buoyant force is communicated as the weight of the liquid displaced, that's why, because rho v is the same thing as m times g. All right, so this density of liquid was given as 1,020 kilograms per cubic meter. We happen to be hanging out on planet Earth, so there's 9.8. And that V sub comes from the fact that that raft was 2 meters by 2 meters by, now here, the part that is below water was given as 0.024 meters. All right, so only the V that is submerged, the 2 by 2 by 0.024. If you take these 3 numbers and get the answer of just those 3 multiplied together, you will get 0.096 cubic meters. I didn't bother to do that. I just showed it to you so in case you do something like that, you'll see what I mean. But anyway, what this is 0.096 times 1,000-ish times 10-ish, which means we're going to take this number and multiply it by 10,000, which means we're going to move that place 4 spots. And really what you get then is the FB is literally this number moved 4 decimal places, 960. And that buoyant force is in newtons. So an ability to do something like that, do ish math in your head, to eyeball stuff, is what I really try to encourage students to do. So again, if you know that this is 0.096, you're going to multiply that by 10, you're going to multiply that by 1,000-ish, that means you're going to move it 4 decimal spots. And that's exactly what you did. So there's part C. Part D then says, all right, let's figure out the gravity of the raft. So what does the weight of the raft then equal? The force gravity of the raft. Well, that buoyant force is 960, which is what we just calculated, the FB. So we have 960 newtons minus the gravity of U. And if you remember, the first part of this equation, the first part of the problem, it said that your mass is 62 kilograms. So if that's your mass, I have to then turn that into a weight, which means I will take 62 kgs, multiply it by 9.8 meters per second squared, 960 times 620, basically. And that gives us a force gravity of the raft is dancing around 352, and that's in newtons. So that's how much the raft itself then has a weight of, all right, because I took the buoyant force, which was calculated here, subtracted the weight of U from that, and those 3 forces add up to nothing. It's based on this. The buoyancy minus gravity minus U is nothing. If I want to know the gravity of the raft, just move that over, and it's buoyancy minus U. All right, so there's the buoyancy minus U is the gravity of the raft, 352. All right, so then part E says, all right, let's figure out what the density of the raft is. So the mass of the raft is the force gravity of the raft divided by 9.8. Well, the force gravity of the raft, we just figured out 352 newtons. I'm going to divide that by 9.8 meters per second squared. I'm going to get some number, I don't know. If I then take that, and that's the mass of the raft, divided by the volume of the whole raft, not just the part that's below water, but take the mass of the raft, divide it by the whole thing. Okay? What I'll do then is take this number and divide it by the volume of the whole entire thing, which was 2 meters by 2 meters. So those 2 dimensions don't change. But now I'm not concerned with the part that's below water. I'm concerned with the entire raft, the height of the whole entire thing. So what I'll do is take 352, divide that by 9.8, then divide it again by this quantity here, 0.2 times 0.2 times 0.09. All right? So you do this, you'll get a number dancing around 36-ish. You can tell that 35 divided by a little bigger than 350 divided by a little smaller than 10. You're going to get a number around 36, 35.9. Then you're going to divide that by this, and your answer for the density of the raft. This is the density of the raft, and it's dancing right around 199.8 kilograms per cubic meter is the density of the raft. All right, the rho R, density of the raft. Again, it's just taking the mass of the raft, dividing it by the volume of the entire raft. But to get the mass of the raft, you got to take its weight, divide by G, then divide it again by the volume of the whole entire thing. All right, so it's a long one, but hopefully it's making sense. Then, part F. Hey, you can't limit yourself. Part F says, all right, what is the maximus amount of buoyancy that this object can exert? The maximum buoyancy is the density of the liquid times gravity times the volume of the whole and entire raft. The volume of the whole thing, which if that whole thing is submerged with just the surface of it, even with the surface of the water. So the density of liquid again is 1025. That was given the problem. We're still on Earth. 2 times 2 times 0.09 meters, the depth of the whole thing. This turns out to be 3,616 newtons, which we're not going to have that many digits. Usually they'll round it to 3,620 newtons is the maximus amount of buoyant force that a raft of that dimension and with its own density, I know, but with a styrofoam raft of that size can hold up that amount of weight. Okay? If that's the case, then what the next question says, well, what is the maximum mass of survivors that this raft can hold? All right, maximum mass of survivors that this raft can hold. Well, if that's the maximum force it can hold up, then that force maximum buoyancy is going to end up equaling the maximum force of gravity that it can support, because the upward force has to be greater than or equal to the downward force in order for this sucker to float. So buoyancy minus gravity still has to equal 0. And that maximum force, then just move that over. The FB max is equal to the FG max of the whole thing, which I went ahead and broke into a mass times gravity. So mg is Fg, and it equals the force buoyancy max. So if I take that F buoyancy max and divide it by g, I will solve for the mass of the whole thing. All right, so that force buoyancy max, 3,620. If you keep all of the digits in your calculator, which is fine, I don't blame you, you can take 3,616. So what I will do is take that 3,616 and I will divide it by 9.8. And you can tell 3,600-ish divided by 10-ish is going to be 360-ish, right? I mean, that you can do in your head. So we're going to be dancing around 360-ish. It turns out this is 369 kilograms. The other way you could do that, though, is to set, okay, that force buoyancy max equal to the mg. The force buoyancy, again, is that density of the liquid times g times the volume of the whole thing. It's the exact same part we did in F. Just put it all together the same way we did in part F. Set it equal to mg. What makes that easier is the g's die. It doesn't matter what planet you're on. And the mass of the whole thing cannot exceed 1,025 times 0.36 now. So it's dancing around 1/3 of 1,000, or a little more than 1/3 of 1,000. So a little more than 1/3 of 1,000 is a little more than 330, right? So this number, again, is exactly the same thing. You will end up with 369 kg. So 369 kgs is the exact same as this. So you got options. All right? So that's the total mass this thing can hold up. If that's the case, then we need to subtract out the total mass minus the mass of the raft will equal the mass of survivors. So if we end up then saying, okay, that's the total mass it can hold up, 369. Well, what's the mass of the survivors? The mass of the raft, if you remember, is its density times its volume of the whole thing, 998 times 0.36. The mass of the raft is about 1/3 of 100. About 1/3 of 100. So 0.36 times 99.8. We're dancing around 35.9 kgs is the mass of the raft. So if I take that number, subtract it from the mass of the whole thing, then I'll know the mass that it can support in addition to itself. Okay? So, this 35.9, then if I take that, 990 times 0.36, 35.9 kgs. If I take what, 369 is the total, minus that, then I will get, or this 352 times divided by 9 is 35.2. It says 35.9, sorry, kgs. Those are two different ways of getting the mass of the raft. That's what I was trying to show you. Two different ways. That's the mass of the raft, that's the mass of the raft. mg divided by g. So the mass of the whole thing. Then the mass of the survivors, if I take 369 minus 35.9, I will get the mass that it can support in addition to itself, which is dancing around 333-ish kgs. All right, so 369 divided by 35, 31-ish, 331-ish, somewhere in there. It depends on how you round. 330-ish. There's an ish kgs. That's the total mass it can support in addition to itself. Okay? And if you want to know how many survivors, then what you can do is go back to the initial part of the problem that says, well, gosh, my mass, or the mass of you, happen to be dancing around, what, 62 kgs? So if this problem asked how many survivors could it hold up, it would be this number of kgs, 330, divided by 62. If they're kgs per survivor, which sounds low to me because I'm 140 pounds, I'm not a very big guy, and I'm dancing around 64 kgs, but anyway, that's the number given in the problem. You're going to say each life raft can hold ish 5 survivors per raft. Okay, so this one did take a while. There's a lot going on. There is, I mean, just remember, but that raft now, don't get confused with the volume that's submerged compared to the volume of the whole thing. Then, again, treat them all like Newton's second law problems. Add up all the arrows. How many arrows do you see? Okay, how many arrows? I don't know either, but they will typically add up to nothing if not, if nothing is moving. If the raft is floating, it's stationary. And then based on that, you got a volume that's submerged. There's the buoyancy based on the rho GV submerged, 960. That's how much is holding the raft up. That buoyancy minus the gravity of you is the gravity, the weight of just the raft. To get the mass of the raft, you take its weight and divide it by 9.8. There's the mass. To get its density, you'll take that mass and divide it by the volume of the whole thing, and you're dancing around 100. Then the maximus buoyancy that raft can exert is the rho GV of the whole thing. So 3,616 newtons, 3,620. So then the buoyancy max minus the gravity of the whole thing would then equal 0. This again means the two arrows, the up arrow of the whole system minus the down arrow of the whole system equals the number of squat thrusts I've done today. And so you then just move that over, mg divided by g. That's the maximum amount of mass it can support, 369. That's the mass of the whole thing that raft can support. But from it, you have to subtract the mass of the raft itself, and that will give you the total mass of survivors it can support. So the mass of the raft is its density times its volume, or it is its weight divided by g. Either one, you got options. You'll get a number dancing around 36. That's the mass of the raft. So you take it, the mass of the whole thing, 369, subtract the mass of the raft, you'll have a number dancing around 330-ish. It's not perfect. Kgs is the mass of just survivors it can support. And if you say each survivor is 62-ish kgs, you can hold ish 5 survivors. All right, so there's those. And again, keep fighting with the physics, folks. It is sometimes a little confusing, but it's pretty easy. It's just a bunch of densities, rhos and v's, and if you're a little lost, it's okay, because these types of things, when you first get used to them, you're just inexperienced, that's all. So just keep fighting with it. Please email me with any questions. We will keep going, and yay, physics.